Moving on to reactions of aldehydes and ketones. First thing we're going to look at is reduction of aldehydes and ketones. And since aldehydes and ketones are oxidation products of alcohols, they can be reduced back to the alcohols using a reducing agent. So let's have a look at this case if we're looking at an aldehyde. If we're looking at an aldehyde, so this is ethanol being reduced to ethanol, and the active hydrogen is here, which is carrying out the reduction. If you're asked to write an equation for this, you need to make sure that you will also balance the equation. So doing this again, CH3CHO plus your active hydrogen in brackets, going to give ethanol. And if you look, you are gaining 2 of these, so you need to balance that with a 2. Looking at a ketone example, if we use propanone, that will be reduced to propan-2-ol, secondary alcohol. And again, that will need, if you're asked to write an equation, you would have to balance that. Again, it's going to need 2 of these active hydrogens. Okay, so reduction is carried out using a source of the H- ion, and the 2 compounds that you need to know about are sodium borohydride and lithium aluminium hydride. And the mechanism that it actually works by is nucleophilic addition. Have a quick look at that. We'll use a generic ketone or aldehyde with 2 R groups, doesn't matter what they are. And we'll use a H- ion. Make sure that you show the 2 electrons here, and it's helpful to put the delta positive and delta negative in there as well, because it helps you to remember what goes to what in terms of electron density. So starting from the lone pair on the H- ion, the electron density, take some of the electron density from here and push the oxygen. And let's look at what that looks like afterwards. Got our 2 R groups here. We've got our H that we've added in at the bottom here, and our oxygen has become O-. Again, it's got a lone pair of electrons itself. At this point now, we need to pick up a H+ ion using this lone pair, and that usually comes from the solvent. And that gives us our alcohol product. So now we need to think about which reducing agent do we choose. We've got 2 possibilities. So we'll start with about NaBH4, sodium borohydride. In this case, this is the most benign. Okay, it's the easiest to handle. It uses the least hazardous solvents. And it can even be done in water. Okay, that's ethanol. In terms of lithium aluminium hydride, much more difficult to handle. It requires an inert atmosphere. So you would have to remove air from your flask and replace it with something like nitrogen or argon. It also requires dry solvent. which is expensive to buy or to produce, and it's also less easily controlled. It can also reduce other groups that are present in the molecule. Okay, through these mechanisms, we can contract our pentanal down. So let's just look at the important parts. Here is our aldehyde group, and we can make the rest of it just C4H9. And we're going to react with H-. Remember that you need your lone pair. You need to put your electron density out into your oxygen. That leaves you with a negative charge and a lone pair on your oxygen. And then we're going to pick up H+ from the solvent. Okay, so leading us to our pentan 1-ol. Let's have a look at pentan 3-ol. Again, we'll just look at the carbonyl group here. We can make this C2H5, this C2H5, so that we're just concentrating on the important bits. Here's our H-, its lone pair, into the carbonyl, out into the oxygen. Use our H+ from our solvent. Electron density goes to that, leading to pentan 3-ol. So let's look at reactions of nucleophiles with aldehydes and ketones. We know that the polarity of the carbonyl group means that they are going to be susceptible to attack by nucleophiles. Let's look at that generic aldehyde or ketone. Okay, so a nucleophile is something that's electron rich. It's going to be attracted to our delta positive of our carbon in an addition type reaction. We're actually going to look at the addition of the Cn- ion, which is generated from something like hydrogen cyanide or potassium cyanide. And because it's a carbon-containing nucleophile, if we add Cn-, then it allows us to make the carbon chain longer. This is quite useful to synthetic chemists. Let's have a look at a mechanism here. I'll just do the general mechanism again. Here's our Cn-. It's very important that you have your lone pair on your carbon to show that that's where it joins on. This is attracted to the carbon, electron density out into the oxygen again, leaving with oxygen with a lone pair and a minus charge, and our Cn has been joined on there. Again, like in the previous mechanism with the H-, that O- actually reacts with the solvent by picking up a H+, and we end up with a product containing a Cn and also an OH group, and this product is called a hydroxynitriol.